Hey, welcome to The Explainer. Today, we're going to talk about something that's maybe the most important idea in all of computing: abstraction. It's this incredible art of building massive, complex digital worlds, not by adding more stuff, but by cleverly hiding the details.
To really kick things off, I love this quote from John Gutag because it just nails it. The whole game is about focus. It's about deciding what is absolutely critical right now and then just forgetting about everything else so you can actually get the job done.
All right, so what does that really mean in practice? Well, in computer science, this is something we do on purpose. We build these layers that hide all the messy complexity, which gives us simpler ways to work with things. I mean, think about driving a car, right? You've got a steering wheel, a gas pedal, a brake. You don't have to think about firing pistons or fuel injectors. That is abstraction in the real world.
Okay, so you might be thinking, why bother? Why is this whole idea of hiding stuff so important, so fundamental to, well, everything we do with computers?
Well, the short answer is the real world is a mess. It's chaotic, and computers, they need things to be clean, logical, and predictable. So by building these stacks of abstractions, we can build these enormous systems by just focusing on one tiny piece of the puzzle at a time. And the beauty is, each layer just has to trust that the one below it is doing its job. It doesn't need to know how.
But, and this is a big but, it's not a perfect system. Joel Spolsky has this famous idea called leaky abstractions. The idea is that sometimes a problem way down in a lower level can kind of bubble up and cause really weird problems in the layers above it. But you know what? The fact that they aren't perfect doesn't change how unbelievably useful they are. All right, to really wrap our heads around this, let's go on a little journey. We're going to climb what you could call the abstraction ladder, starting right at the very, very bottom with the actual physical hardware. So, at the very bottom, I mean the absolute ground floor, you've got the hardware itself. We're talking about the CPU. It has these tiny, super fast memory spots called registers. And inside those, you have these little circuits called flip-flops. And each one holds just a single bit, a 0 or a 1. And then the arithmetic logic unit, the ALU, that's the part that does the math. It grabs bit from the registers, crunches them, and puts the answer back. You literally can't get any closer to the metal than this. The thing is, we humans, we're terrible at thinking in just zeros and ones. So what did we do? Over decades, we built layers of language on top of that hardware. First, you had machine language, just pure binary. Then came assembly, which gave us little shortcuts, little names for the binary commands. And finally, you get to high-level languages like C or Java, which let us write code that's much closer to how we actually think and talk. And here, right here, is where you see the magic happen. You look at that line of Pascal code. To us, it's dead simple. 1 plus 2 is 3 times 5 is 15. Done. But to the computer? Oh man. Under the hood, that one simple command explodes into dozens of tiny steps. The computer's got to convert everything to binary, break the math down into little assembly instructions, shuffle bits around in registers, and then finally find where A lives in memory and stick the result there.
I mean, can you imagine? Without that abstraction, the programmer would have to do all that grunt work every single time. Each new layer we build makes programming more powerful, way more accessible, and it frees us from having to worry about the specific hardware we're running on.
Okay, so we've seen how this works for languages. But what happens when you blow this concept up to a massive scale? What if you're trying to tame the complexity of thousands of computers all working at once?
Let's look at a system like MapReduce, which was pioneered at Google. It's built to handle absolutely enormous data sets. We're talking petabytes of information spread out across huge clusters of machines. Now, you could try to manage all that yourself, or you can use a beautiful, powerful abstraction.
So if you look at how this works, it's pretty genius. You, the programmer, you just write your code and send it to one main master computer. That master then takes your job, chops it up into little pieces, and farms it out to hundreds, maybe thousands of worker machines to all chew on their piece at the same time. The map-reduced system coordinates the whole symphony, hiding all that unbelievable complexity from you.
And here's all the stuff you don't have to worry about. splitting the data, scheduling the jobs, handling it when one of the machines inevitably fails, managing all the chatter between the computers, and then pulling all the results back together at the end. It's insane. This one layer of abstraction lets a single person conduct an entire orchestra of computers without getting lost in the weeds.
So this all sounds amazing, right? But it brings up a really important debate that's happening in software right now. Can you have too much of a good thing? Is more abstraction always the answer? There's this idea called Gall's law, which is basically a warning sign. It suggests that every complex system that actually works started out as a simple system that worked. It says we get into huge trouble when we try to design some giant, super abstract system from the get-go, instead of letting it grow and evolve naturally. And if you talk to any developer, they'll tell you they see this all the time. This Reddit comment just hits the nail on the head. It's this problem called over-abstraction. You see people creating all these extra layers and interfaces, not because the problem needs it, but because, well, that's what the tutorial told them to do. And this isn't just about messy code. The risks are huge. You can end up with really inefficient, bloated software. But maybe even more worrying, if we're not careful, we start to raise a generation of developers who don't really know how anything actually works underneath all those comfortable layers.
Okay, so how do you avoid this trap? Well, a lot of seasoned developers have this great rule of thumb, sometimes called the rule of three. The first time you write some code, just write it. The second time you need to do the same thing, you just copy it. You resist that urge to be clever. It's only when you find yourself needing that same pattern for a third, fourth, or fifth time that you finally have enough information to build a good abstraction that really works.
And that, right there, is the daily tightrope walk for anyone who writes code. You're constantly trying to balance making things clean and easy to reuse with not building a confusing mess of layers that nobody, including you, understands a month from now. So when you boil it all down, what are we left with? Abstraction is, without a doubt, the engine that built our modern digital world. But every layer we add comes at a cost. So here's a little challenge for you. The next time you open an app on your phone, just for a second, think about the incredible, invisible stack of abstractions holding it all together. And ask yourself, what amazing capabilities are we gaining, and what understanding are we maybe losing in the process?